Hello students, today I will start the second part of Introduction to Electrodynamics. Uh, we will follow the book of Griffith, and actually this is the second part. In the first part we studied about the electrostatics and magnetostatics, where we study the charges at rest and the current which is constant. So this was the previous case, and now I am going to discuss the second part of this course, and this will start from the chapter number 7. So here we will study the characteristics of the charges, which they are moving non-static position, but the charges is in motion. So here if I write down, this is the lecture number first, and this is actually electrodynamics, chapter number 7, electrodynamics. And here we will study the charges, the characteristics of charges when they are in motion. So this course is related to electrodynamics. Here the first part that I would like to study is electromotive force. And this is 7.1. And here 7.1.1, the first topic is the Ohm's law. So what is Ohm's law? Here I will start from the electric field and current, and the relation between the current density and force per unit charge. So here according to the Ohm's law, the current density is directly proportional to the force per unit charge. Here the current density is directly proportional to the force per unit charge. So the current density can be represented by J, and the force per unit charge can be represented by F. Let's suppose F. Then it means that J is directly proportional to F. So this is directly proportional to this, and further if we remove the proportionality, then we can get sigma F. Here sigma is, this sigma is conductivity. It should be noted that this sigma, previously we have used this for the surface charge density, but here don't confuse, this is just a symbol. So here J is equal to sigma F. So here sigma denotes the conductivity of the material, and it will change from material to material. Different material have different conductivity. So the value, if I write down, I will remove this. The value of conductivity varies from one material to another. It means that different material has different conductivity. Okay. The reciprocal of conductivity is called resistivity. The reciprocal of conductivity is called resistivity, and it is denoted by rho. So previously we have used rho for the volume charge density, so don't confuse between the symbols that now in electrodynamics we are using here rho. This is for the resistivity, and this is that surface volume charge density, and sigma is also the conductivity, and is that surface charge density, so don't confuse. If I write down this point, here do not confuse, because previously sigma was used for surface charge density, and rho for volume charge density. So don't confuse between the symbols. Okay. The conductivity of metals is very high, where for insulator. The conductivity sigma, which is approximately equal to 0. And it should also be noted that the force that drives the charges to produce the current could be chemical or gravitational etc. So it should be noted that the force that drives the charges, for example, if we consider a battery, cell battery, then it can drive the charges by a chemical force, and there are some other examples of the source, the force that drives the charges. I will discuss this later. For example, F, the electromagnetic force do this job, then if we consider the force, which is electromagnetic force, then we can write down F. This is electromagnetic, means there's electric force and the magnetic force as well. Then we can write down E plus V cross B. So this is actually the force, the force per unit charge. So this is equal to electromagnetic force. Then previously we have defined J, which is equal to sigma F. Then if we write down, if we put the value of F in this equation, then J, the current density, must be equal to E plus V cross B. Now the point is, if V cross B, if V is very, very small, after the charges which is moving at a very small velocity, so it means the second part of this equation must goes to 0. So V cross B, if V is very, very less, then we can write down this part must go to 0. And then J will be equal to sigma E. So this is J, the current density, will be equal to this. And actually this is the discussion in this chapter. This is the discussion in this chapter. And this equation is called Ohm's law. So obviously in previous classes, you have studied about the Ohm's law, and the Ohm's law, which is a very famous equation, V, which is equal to IR. So I think this is little bit confusion. Why this J is equal to sigma E is the Ohm's law. So there is any similarity between this and this. This is also Ohm's law and this is also Ohm's law. So this I would like to discuss the relation between this and this, how we can obtain V is equal to IR by using this Ohm's law. This is also Ohm's law. This is also Ohm's law. We can derive V is equal to IR from this. So actually this is the same. These two equations are the same. So how we can get this equation? We have to discuss two examples of chapter number 7, and then we can get the result why we can say this is Ohm's law as well. So let's discuss the two examples. Example number first. This is actually a very long statement of this example, but it is very easy to understand because it tells us a cylindrical resistor of cross-sectional area A and length L is made from material with conductivity sigma. I will consider this point, a cylindrical resistor. Let's say this is a cylindrical resistor, and it has length L and cross-sectional area A, and here the cross-section need not to be circular, but I do assume it is the same all the way down. It is not a circular, but it is in the shape like this. And if we stipulate the potential as constant over each end, and the potential difference between the end as V, what current flows. It tells us here if the potential V is equal to V naught, and here if the potential V is equal to 0, and here the potential V is equal to V naught. But the potential is constant here. From one end to another end, the potential is constant. Also here E, the electric field, is also constant. So how to solve this equation, this example? I want to review this. You can see this in your book as well. So this is example number 1. So how to solve, how to find out the current here as the current density. We know as solution. We know the current density. And current density can be defined as current per unit area. So this is current per unit area, we know. This is from the previous knowledge. And we can obtain the current I, which is equal to JA. If I represent this is equation number first. And then we also know the current density. Also, the current density, we know about this, which is equal to J is equal to sigma I. This is the Ohm's law. So J is equal to sigma E, putting the value of J in equation number first. Putting the value of J in equation first. Then we can get I, which is equal to J sigma E and A. Now, what is E here? How we can look, we can find out the value of E. What is electric field? How we can calculate the electric field in this configuration? So we need here E, where we need for E. How we can calculate this? From the previous knowledge, this is equation number 2. From the previous knowledge, we know the potential difference V plus minus V minus, and this can be defined as E dot dl. And here E is constant and V is equal to dl minus E is constant and dl, and integrating this length we will have L. So it means that V, which is equal to minus E L. So this is actually the general situation. This is the general situation. But now we have the potential V is equal to 0 here, and this potential is equal to V naught. If we use this condition, then we can get V is equal to 0 minus V naught, and which is equal to how we can get the result minus E dot dl. So it means that minus minus cancel and we can get E L, and E can be derived as L, volume per unit length. So actually this E is equal to I, which is equal to sigma A, or this V divided by L. So here we should note this equation. And here this sigma, this is the reciprocal of the resistivity. So if we write down, so actually from this example, this is the current, this is the required result that we have obtained. So this is the required result. But now I want to write down this in another form to show some other things. So actually this is the required result. I want to write down this in another way, because sigma is equal to 1 over rho, then F, I write down I, which is equal to sigma 1 over rho and A divided by L and V. So from here, this thing, if this term, if I take this and move from right hand side to the left hand side, then we can get I rho L divided by A, which is equal to V, and this term is equal to R. This is the resistance. This is the resistance. So we can say that I R, which is equal to V, R, V, which is equal to I R. So we start from sigma is equal to J. We start from J is equal to sigma E, and we get the result V is equal to I R, and this R, actually this R is the resistance of the material, and this resistance depend upon these kind of things. This is the property of the material. It depends upon the length. What is the length of the material? So if the length is greater, then there will be a greater resistance, there will be a high resistance, and if the area of the material is very high, then the resistance will be low and inversely proportional. This is the resistivity. So actually J is equal to J, which is equal to sigma F. This is the Ohm's law, and we can get the generalized, the famous equation V is equal to IR. Actually this and this remains the same, but this Ohm's law show that V is equal to IR, the characteristics of the material, how many factors that involve in this resistance. So actually this is a very important point. Now the other question that I would like to solve, this is example 7. This is the second example and it tells us two long coaxial metallic cylinders having radii A and B. These are two long metallic cylinders. One has radius A and the other one has a radius B. And these are separated by a material of conductivity sigma. This has been separated by some material, and this material has some conductivity sigma. If they are maintained at a potential difference V, if they have a potential difference V, what current flows from one to the other in a length L? If this metal has length L, then what current is flowing from one end to another end? So here we also need to find out the current. But how to find out the current? Let's see the solution. First of all, solution of this example. First of all, we are looking to find out the electric field, and in this configuration, what will be the electric field, and then we may proceed this problem further and we'll find the current. So to find the current here, to find the electric field here, we need to find out the Gaussian surface here. We use the Gauss's law to find the electric field. So this is the Gaussian surface. This is the Gaussian surface having radius r. Then to find out the electric field, then the electric field through the Gaussian surface. We have to use the Gauss's law. For example, E dot dA. This is the Gauss's law, which is 1 over epsilon naught in the total current enclosed. This is the famous Gauss's law that we can use to find out the electric field. So here E is constant in this configuration, so this can be write down this, and 1 over epsilon naught, and Q enclosed. This is actually the charge and having length L. So what will be the charge density? So the charge density we can define lambda, charge per unit length, and here we can find out lambda L. So this is the charge enclosed, and we can put here lambda L. And what is the area, enclosed area of this Gaussian surface? So this is actually a cylindrical shape. So here the area must be 2 pi having radius r and length L. So this is 2 pi r L. And further lambda L divided by epsilon naught. And here you can see this L and this L can cancel out, and finally we can find out electric field, which is equal to 1 over epsilon naught lambda divided by 2 pi r, and r is a unit vector. You can also write down like this. So this is the electric field that we have derived. Now further I want to erase this. Now what is the current? Now the current through this configuration, current may be defined as, actually charge density may be defined current per unit area, but for the whole system, if I define the current for this whole system, I can write down J dot dA. So this is the total current in this configuration. And now we know J from the Ohm's law, sigma E, J which is equal to sigma E. So I must be equal to sigma E dot dA. And we also derived the electric field. So putting the value of this electric field here, then the current must be equal to sigma and 1 over epsilon naught lambda divided by 2 pi r, and r is a unit vector, and here I can write down r as a unit vector and dr. So r dot r, this will be equal to 1, and further this sigma, this thing, lambda and 2 pi, these all things are constant. So I will write down sigma lambda divided by 2 pi r and epsilon naught, and this will be equal to dA integration. Only we will have dr and 1 over r. Sorry, this is actually the case. This okay, please I will write down this like that. actually this is dA, not dr. So these things will come out and we will have dA and I, which is equal to sigma lambda divided by 2 pi r and epsilon naught. And what is the area of this configuration? This is 2 pi r l, and here 2 pi r and 2 pi r will cancel. These terms will cancel out, and we will get sigma L sigma lambda L divided by epsilon naught. So this is the current. Now this equation number first. This is not complete now because we are interested to find out the relation between I and V, how we can obtain, because there is some potential in this configuration. So how we can find out the potential? So let's see. As we know, the potential difference, the potential may be defined from B to A, and this is E dot dl. We can define the potential like this, and we can also write down to reverse the value of A and B. Then the negative sign will vanish, and A, B, and E dot dl. So, and how we can find out the value of V? So we need to put the value of E. Previously we have calculated the value of E, and we have to put this value of E in this equation. So V is equal to, from A to B, this we have calculated previously, lambda divided by 2 pi r, and r is a unit vector, and here dl. So dl is a length, so we can write down this in terms of dr. So let's see, v, which is equal to, from A to B, in some things there are some constants, lambda, epsilon naught, and 2 pi. Then lambda divided by 2 pi epsilon naught. These terms are constants, so we will have only 1 over r, and r is a unit vector, and r dr we can write down like this. So what will happen if this equation, if I write down here, because I don't want to remove this equation, epsilon naught, this equation 1, and now I want to erase this. Okay, so r dot r is equal to 1, and we can get 2 pi epsilon naught, and A to B 1 over r dr. So the integration of this kind of situation, 1 over r, this is equal to natural log of r, and we will put the values. Then v, which is equal to lambda divided by 2 pi epsilon naught, and log of r and a b. And if we put the values, then lambda divided by 2 pi epsilon naught, and log of b minus log of a, and further we can write down this as equal to lambda 2 pi epsilon naught and log of b divided by a. This is a conventional method that we can write down like this. So further we can say that v, which is equal to lambda divided by 2 pi epsilon naught and log of B divided by A. So here from this equation we have to calculate lambda. We have to find out the value of lambda, and this lambda, the value of this lambda, then we can put in equation 1 and then we will see what will happen. Let's see. Lambda can be written as 2 pi epsilon naught and divided by log of B divided by A and V. So this is the potential. Putting this value, the value of lambda in equation number first. So what will we have? Let's see. I, which is equal to sigma L divided by epsilon naught, and the value of lambda is equal to 2 pi epsilon naught divided by log of B divided by A and V. So here sigma, this is actually the reciprocal of resistivity. So if we put the value of resistivity this and then compare these values, let's see, I, which is equal to L divided by rho epsilon naught, and this is 2 pi epsilon naught log of B divided by A and V. This whole term, if we move this from if we move this term as a whole to the right hand side, then we can get the value of I. Let's see how to maybe we can cancel the epsilon naught, and finally I will write down the current this will be equal to if we move this term to the left hand side. So we have rho log of B divided by A and divided by 2 pi L, and which is equal to V. So actually this thing now in this example, this is equal to this whole term, this is equal to R. So V, which is equal to IR, and this R now depends upon the length and the length only. I think the natural log of B, the radius of A and B. This also depends upon the radius A and B. So we can get the Ohm's law, V is equal to IR. So actually what is the structure characteristics of the material, the resistance tells us about that characteristic. So we can say like this. The unit of resistance, maybe you are familiar the resistance as measure an ohm like this. This is called ohm, and 1 ohm, which is equal to 1 volt 1 ampere. So we can define the ohms like this. Welcome back. The next topic of this lecture is electromotive force 7.1.2. So to explain and define the electromotive force, let us consider we have a battery, and this battery is connected with some wires, and we have shown a bulb. So if these wires are connected with this bulb, then we can get some light. So how to define electromotive force? We consider, let's write down, consider a bulb is connected with a battery through a wire. As shown here. Now there are two forces. There are two forces involved in driving current around a circuit, such as the source, and it is called Fs. Let's say a battery, and electric field E, say wire that can communicate the influence of the source. So I have write down that, let's consider we have a battery, and this is we have a bulb, and this bulb is connected with a wire with a battery. So there are two forces involved in this process. One is the source, the battery, which push the electrons in the wire, the charges in the wire, and this is called the source. This we can denote this for Fs, and the other force is the electric field. This is the electric field that wire say wire that can communicate the influence of the force of the source. So these two forces has been involved in this process. So mathematically, if we write down this equation, that the total force involved here, the source for electric field, and this can be shown as in equation 1. This is the total force, this is the battery, the source, the force provided by the source, and this is the electric field in the wire. So the thing is clear. Here Fs can be different things. Fs, the source, may be of different things, not only the battery, because if I write down that we have many other sources that can flow the charges. These included, for example, if we consider the battery, number first is in a battery. If we consider a battery, then what will happen in the battery? It's a chemical force. It's a chemical force provided by that battery. It may have another thing is in a piezo electric crystal. Actually, this is the mechanical pressure. Mechanical pressure is converted into an electrical pulse. Number third, in a thermocouple, it's a temperature gradient that does the job. These are the different sources that can influence the charges. Last one is in a photoelectric cell. This is actually, it's a light that can perform this kind of job. So these are different sources. Fs, not only the battery, it may a piezoelectric crystal, it is a thermocouple, it may photoelectric cell. So these kind of things can provide the source. So now what will happen if we write down this in a closed loop? So this is equation number first, and for a closed loop, this equation 1 can be written as, if we write down for a closed loop, f dot dl, this is a closed loop, then this must be equal to, for a closed loop, fs dot dl and plus, for a closed loop, E dot dl. So the last term, this term for a closed loop, this part will be equal to 0. According to Ampere's law, for a closed loop, this total term may be close to 0. Ampere's law, this may goes to 0 for a closed loop due to Ampere's law. Okay, so now this equation, this is equal to 0, then we may write this equation in the form of fs dot dl. And this right hand side, we may represent this is E and EMF. This is called electromotive force. So the electromotive force, this electromotive force EMF, which is equal to F dot dl. Now, if the source is a battery and this F, this total force, if we want to define this total force, then last time we have discussed that J, F is equal to J is equal to sigma E. Last time, this is the Ohm's law. This is the electric field. If we replace E by F, then J will be equal to sigma F. And from this equation, F, which is equal to J divided by sigma. So put the value of F in this equation. So this electromotive force must take the form as J divided by sigma dot dl. And we also know J, current per unit area. This is called J. So we may write down as J is equal to current per unit area. So further, if I write down this current per unit area into sigma and df. Okay, and now this EMF, which is equal to, if current is taken outside, then this is equal to dl divided by A and sigma. And this integration term, which involves length, area and sigma is the reciprocal of resistivity. So it means that this term is nothing but this is R, the resistance, which depends upon the length, area. So EMF, which is equal to IR. So we can get this, the Ohm's law, just like Ohm's law, EMF. This is actually the electromotive force, which is equal to IR. So this is the final equation of this electromotive force. So electromotive force is equal to IR.